Yeah, the title of my talk today is Natural Language Processing for Information Systems Research. Normally, I'm not such a big fan of like having method A, B, C for IS research, uh, although I'm also have written kind of these papers, but I try to really look at natural language processing in general. I also have a little bit of a technical background. Here and there, I'm publishing in computer science outlets, conferences, and journals. Um, and yeah, let's go. So yeah, Ann-Kathrin has already introduced me. I'm the professor of information systems and data analytics at Paderborn University, which is kind of in the northwest of Germany. Um, I did my PhD in Münster. It's not too far away from here, from Paderborn, just in 1 hour. Then I spent some time in Liechtenstein in Jan von Borke's group as an assistant professor, and also 3 years in Copenhagen at the ITU. So maybe some of you have been at ISIS when it was in Copenhagen, have seen it. So I just left when we won ISIS. I thought it's time to leave before I have to organize this thing, and then went to Paderborn. So it was kind of a homecoming to the region where I grew up since 2018 now. And yeah, my general interest, so that you can put me into a box, is data-driven decision making. So that's kind of the phenomenon I'm focused on. But I and also in my group, we have different approaches to the topic. One is maybe more design science oriented, and one is more behavioral. On the design science side, it's the design of and evaluation of the data-driven decision making using different methods and data sources and different applications, currently mainly in energy, but also in finance and maybe an exotic topic of sports. So how can we improve decision making in sports using data and analytics? So that's really where we design solutions and evaluate those solutions to novel problems. And on the other hand, I'm also interested in more the meta view of it. So what happens when companies or individuals adopt data-driven decision making on various levels. So at the level of individuals. So like maybe you are into research on algorithm aversion or appreciation. I think it's a big stream in IS research, and or nudging, for example. So that's at the individual level, but also at the organizational level. So what are factors that are deciding whether companies adopt data-driven decision making or don't? What is the business value? Can we measure business value? What are consequences at the economic level, for example, for your job, your future job? Will it still exist? So that's more behavioral IS research. And I'm actually applying natural language processing in both of these. So if you look at the design science side, it's about developing and evaluating novel NLP systems, like large language models, of course, nowadays. And on the other hand, I'm more using it as a research instrument, as a measurement instrument, for example, in econometric research, where you want to incorporate text data maybe into your regression models. And then there's also the question how to do that. And that's another spot where NLP can be used in IS research. Okay, so much for the framing. The agenda for the next maybe 60 minutes or so, but as Ann-Kathrin said, I'm happy to take questions at any point, and we can discuss at any point in time. So don't have to wait until the end of the presentation. I first want to talk a little bit about the history of natural language processing. That's a difficult topic because it's moving so fast right now. You know, ChatGPT is not even 2 years old. So I still have papers under review where we have used methods which I would say are outdated nowadays. But yeah, it's still in the review process, and it happens that now reviewers write like, why don't you use large language models for it? And I say, yeah, you know, at the time we submitted this, they did not exist as we know them now. So that's a problem, I would say. That's really a challenge for doing research in this area. And then I want to go a little bit into the theory or technology, looking at some approaches to do natural language processing. And I picked the topic of sentiment analysis. I know that one or two of you wrote emails that you are interested in detecting emotions in text. So sentiment analysis would be one of such ways to do that. I think it's something everyone has a basic understanding what sentiment analysis might be. And yeah, over the last, let's say, 10 years, if you look at the IS research papers, we have seen different approaches. And I will start with a symbolic rule-based approach, then going over to a more statistical approach, and then in the third iteration or generation here, deep learning, neural networks, language models, as like the current state of the art. And then in part number 3, I want to give you a live demo. Hopefully it works. I will share the script with every one of you. It's actually public, so when you have my slides, you can click on the link and it should open there, and you should be able to execute it right there on Google Colab, which is a collaborative solution for developing Python code online, where I want to demonstrate all the 3 generations using a data set about airlines. I think everyone of us has an understanding about like what you might tweet to your airline and how that is maybe related to sentiment analysis. Okay, so let's dive into the history. Yeah, this, I mean, you have seen slides like this where we talk about the exponential explosion of data. You see this slide is almost already 10 years old. The curve will continues like this. But what I find more interesting here in general than the sheer number is the type of data. So if you look at the color coding of these bars, you see that most of the growth in data volume comes from unstructured data and not from typical structured databases. So here with databases, I mean the classical applications like maybe in financial, human resources, payroll processing, marketing, etc. So numerical data, which you can easily fit into a database, into a spreadsheet. But instead, the growth is coming from unstructured data. This includes text data, this includes also images, videos, audio. And in most of these, natural language plays a big role, even in video and audio, of course. And that has been largely neglected for years. I mean, it changed over the last couple of 2-3 years, but before that, you can look into research and into papers, but you can also go into industry and talk to companies. Most of the companies would have not analyzed that data for a long time. So it's really an irony that maybe 80% of all the data is unstructured, comes from the internet and most companies spend 80% of their efforts to just analyze their internal, nicely structured numerical data from accounting or similar applications. So text analysis is important because it can really unlock a huge potential, but it's also difficult. So first of all, compared to numbers, text is messy. So I would not say that it's completely unstructured. We always say it's unstructured data, but to be honest, probably semi-structured would be the better word here. However, the structures are very different compared to numerical data. So in numerical data, what you see here on the top, we are used to have it in a spreadsheet-like format, where we have observations in the rows and variables describing these observations in the columns, and then we have values which are well defined. On the other hand, if we have text data, we have something like document structures, headings, abstracts, paragraphs, etc. So there's some structure. And also at the micro level, of course, I mean, we have grammar. Grammar is nothing else than structure. So it decides how we can build valid sentences from words, for example, in what order they have to come, for example. But these types of structures, they don't match. So if you want to use mathematics or statistics on your text data, you have the challenge, how do I fit data from at the bottom here, which is has a document structure or maybe grammar into this table-like format. And as you will see later on when I demonstrate some of the methods, that's exactly what they are doing. So a lot of natural language processing is about transforming text data in such a way that you can then apply normal statistics on it. Next challenge is it's uncontrolled. So if you think about it as a vocabulary, if you look at the vocabulary of all the numbers, I mean, they were well defined, and no new numbers are invented. On the other hand, if you look at text, it's constantly changing. Language is changing. You see here on the left-hand side a histogram of the frequency of words in the English language. So per 1 million words, so I is the most frequent word. And then if you look at these I, the, to, you, my, and me is that, of, etc. So what you see here is the most frequent words are really not interesting. So these are often pronouns, etc. So function words, which you need in order to build valid sentences, but they don't bear a lot of meaning. So you really have to go into the long tail of this distribution of words to get to those words which are probably interesting for your topic. So it's not a solution to say, okay, it's so uncontrolled, there's so many words, just let's focus on the most frequent ones. That's typically not really interesting. And then on top of that, there are new words appearing all the time. So slang, for example, abbreviations. You might work in a certain industry or with company data, and they have their abbreviations, which you cannot find in any dictionary at all. So that is a challenge, this constantly changing nature of language. And the last challenge I've listed here is the meaning of language or text is more difficult than the meaning of numbers. So here, this is only on the word level. So we have these well-known phenomena like synonyms and homonyms and heteronyms and heterographs, etc. Some interesting examples which you can find here in this figure. And you can imagine how difficult it is to write algorithms which can distinguish between desert and dessert, although it's like exactly written in the same way, and it's only about the pronunciation. So this is ambiguous, and then we have other things on top. Right? So if it's not only at the word level, but like level of paragraphs or texts, you have things like irony, sarcasm, etc. That makes it even more complicated. So that's another challenge we have to deal with when we do natural language processing. So if we look at the side of solution here, solutions, what are the solutions to these challenges? And the NLP field is actually already quite old. It started after the Second World War, also directly from development from the Second World War. Alan Turing here as a key figure here. And in the 1950s, which was the inception of the field, where people more or less just like formulated visions. And you might be familiar with the Turing test, which used to be a test for whether we have reached AI or not, where it was like just like a mind game or so. Can you distinguish whether you're talking to a machine or a human, just judging from the text alone? Similarly, there was Weaver's memorandum, which was more about machine translation, etc. So these were the basics. And then in the 1960s, the first era started with what is called symbolic natural language processing. So this was very much, I would say, a bottom-up approach, very much driven by, the idea was if you analyze grammar, text from a grammatical perspective, you can solve the problem. So Noah Chomsky is one of the key figures here. And the idea was we are parsing natural language according to grammatical rules. We can write down the grammatical rules. Maybe on top of that, we can also write down, let's say, ontologies of domain knowledge, maybe in medicine or in legal, and then we can build machines. So ELIZA was one of the first, or was the first chatbot developed probably, and it was a psychologist. You could chat to a psychologist there, and it was really, and you can still try it out online, and it really had the impression that you are chatting with someone, that there was an agent or individual on the other hand, or other side of the screen. However, what ELIZA was doing was just applying some very simple rules. So when you, for example, say, I have a bad relation to my father, and then ELIZA would pass this text, would find the word father, look into a dictionary or ontology, and analyze what are semantically related or grammatically related words. For example, family. And then ELIZA would answer, say, tell me more about your family. That would be the next question. Yeah? And then you almost feel understood. And then you write something else, and it always asks a question back. It never gives the answer, basically. Some people would argue that it's what psychologists do, maybe. That's why this prototype was quite successful. It was not so successful when they had other versions, for example, imitating a lawyer. There it was a little bit more difficult. People formulated this as the knowledge acquisition bottleneck. So the rule base you need for really a proper expert conversation is just enormously big. And then also the rule base you need to represent common sense, etc. There was people in the beginning thought we can just write down all the rules of a medical doctor, for example, because that's what they do. They follow rules that they have learned at university. But people gave up after some years. And we had this AI winter where the vision of artificial intelligence and NLP was really seemed very far away. But then in the 1990s, we had a change. The internet came, and the internet produced just enormous text data sets. The first time that we had really access to large data sets, also often in multiple languages. For example, the European Union has to translate all their debates and legal documents into, I don't know, about 10 different European languages. So these were really precious resources for the NLP community, for example, to build translation systems. And so the focus switched from a rule-based or knowledge-based approach to a statistical approach. And that's to say, like, let's forget about all those rules. Let's just look at associations between words, and maybe that helps us. So supervised machine learning is the approach here, and I will come back to that, how that works later on. And as a kind of, I would say, it's just an extension of the statistical NLP approach is then what happened after year 2000, maybe 2010, where with all these deep learning neural networks, they are basically still following the statistical approach, but with different algorithms. So with more computing power and even bigger data sets, people were able to train even bigger models. Which do not take so many shortcuts in processing natural language. And this is where we still are. So you see here transformers and large language models as the last bubble here on my timeline. And that's the current state of the art. And what I want to do now, I want to show you one concrete method from all of these three generations. So starting with the symbolic approach, and to be honest, I forgot to do it. So I wanted to go on the AISE library and look for the latest papers still applying such an approach. So because you might now say like, hey, Ollie, this is 1960s. You said this is from the 1960s, but honestly, this is really very common. So if you go to ESIS in next month, I think we will still see some presentation following this symbolic rule-based, knowledge-based approach, which, for example, builds on dictionaries. My application here is sentiment analysis. So roughly this defined sentiment analysis is the computational analysis of opinions in text. Anything can be opinions, emotions, sentiments, subjectivity, etc. So you have seen all these applications. So I think every time there's an election in the United States, someone claims that they can predict how it goes by analyzing tweets, which are then like referring to some of the candidates. It's also very famous in marketing. How do the customers like my new cafe latte, which Starbucks is selling or something like that? Are they writing about it online? And when you take a dictionary-based approach, it goes a little bit like this. So I give you a couple of seconds to scan the diagram. This is the simplest possible method, but it is still often applied. So we assume that we have a document collection. So maybe social media posts, 10,000, which you have downloaded somewhere, or you have collected yourself. Could also be a collection of papers or news articles or whatever. What you do if you have your corpus here, you go through it document by document. And for each document, you go through the document word by word from end to end. So the first task is to split your document into words. So this is typically, you can take the simplest approach, which is splitting by white space. So if you have a long string representing the whole document, you split by white space, and then you have a list of words. And then you go through this list of words, and you look up every of these words in a dictionary, in a sentiment dictionary. Hopefully you can find one of these dictionaries online, that some linguist has created it for you. If you don't have such a dictionary, then yeah, you might have to create your own, and that's probably another project on its own before you can apply it. These sentiment dictionaries, I will show you a couple of them on the next slides. It's basically a list of words, and each word has a score. So the simplest dictionary would be just positive or negative. And for example, you have a word which is a +5, which is very positive, and going to -5, which is very negative. And then you just sum up the scores of all the words you find in the dictionary. Of course, most of the words you will not find in the dictionary, so they implicitly get a 0. And then at the end, you have a score for your document. And that's your sentiment score, whether it's a positive or negative. Yeah, the whole message is positive or negative. Can anyone see any challenges or problems with this approach? The chat. French people. Yeah, okay. Good. Irony is another one, yeah. So what is irony? It's probably irony is if you say something negative with positive words, right? Or vice versa. Maybe that's a working definition of irony. So that could be limited to words provided in the dictionary, of course, yeah. So maybe you are working on a specific topic, let's say financial. You want to do sentiment analysis in a financial application, and then there are certain words like bullish or bearish, which only have a meaning inside the finance world, but not in the normal world. So the question is whether that's in your dictionary and whether that has the correct score. Even simpler problems we might have here. We are processing it word by word, just so we assume all the words are independent of each other. So what's the most simple problem we might run into here? Negation, exactly, yeah. So this is not good, this is very good, this is good. So they might get all the same positive score here, if you really follow the algorithm you have seen here. Okay, let's close the chat window. So let's talk a little bit about these dictionaries. So the dictionaries yeah, typically are rooted in some psychological frameworks. So you have Ekman's basic six emotions, for example, or here Plutchik's wheel of emotions. I chose this one because I think that's probably the nicest picture of a theory I've ever seen. So this is a theoretical framework where you have 8 basic emotions, and every emotion comes in 3 different levels of intensity. So here, for example, we have a positive emotion, the yellow one of serenity, joy, and ecstasy. So the most extreme level is in the middle. So you have then lots of emotions here, and basically what people have developed dictionaries which contain words for every of the boxes or every of these fields you can see in here. Um, so some concrete dictionaries are, for example, NRC, that's built on Plutchik's Wheel of Emotions. Contains about 14,000 words. They are classified, each of the words is classified into 8 emotions, so the 8 basic emotions of Plutchik, not the levels of intensity. And on top of that, they are also kind of double categorized, also whether they are positive or negative overall. And then there are others. Centi-strengths used to be very popular because it was tailored to language from the internet. Veda is something which I have seen very often in IS research as an approach, or the linguistic word count, Livig, or actually it's called Luke. It's from Pennebaker, a famous psychologist who has developed that. That's a closed source system, and there are, of course, other vendors which are offering closed source solutions where you can basically pay for it. So here you see the example of NRC, which builds on Plutchik. So you can see here the words, the size of these rectangles represents how many words you have in each of the categories. And if you, for example, will click on anger, you see on the right-hand side all the words in the anger category. And what you also see is that you don't have the words in their dictionary form, but also, so for example, sometimes in past tense or ing form, etc. So that's another challenge you have to battle here, whether you can really find the words you're looking for in the dictionary, because all the inflections of words come into play. So you probably either have to do some pre-processing either on your text side, or the provider of the dictionary has also done that for you already, as you can see here. Vader, the one which is quite popular in IS research, is a little bit smarter than the algorithm I have shown you on the first or a couple of slides ago. So Vader has some heuristics or rules to handle, for example, negation. So it will look in English language whether there is a negation just in front or, of the word you're looking for, like not good. It can also handle contractions like wasn't good. It wasn't very good. So to recognize that this is a negation. It considers punctuation. So it's basically heuristic. So someone says, if you have 3 exclamation marks at the end, it's a +1. It's like a little bit more. Why it's a +1 and not a +2? So that's up for debate. Yeah. Similar with word shapes. If you write everything in capital letters, it's intensified. Then it also knows, for example, emojis and emoticons, which, of course, in the internet world are very important. I really don't know how people keep track of the meaning of all the emojis, whether they are so well defined or not. That's a question. But that's a little bit better than my simple heuristic, and you will catch some of the cases like negations, modifications of your adverbs, adjectives. Okay, so that is basically the symbolic approach. That's what you do. So if you want, you can say you're counting words. You're counting words of certain categories. And then in the end, you are aggregating everything to the document level. Another problem you have in this aggregation is that you can have, for example, a document which is half positive and half negative, and the end result will be neutral. If the first sentence is a +2 and the second is a -2, the result, if you, for example, use Vader on that, it will be a 0. So that's another challenge. So maybe you want to keep those two scores separated if you're working with dictionaries. I think the dictionary approach is quite popular because it does not require a lot of preparation. If you have a dictionary you can apply. So if someone has used a dictionary or developed a dictionary which fits to your application, you might want to reuse that. What is a little bit problematic that I often don't see, that the people don't question that or are not critical enough with their dictionaries, and they are just reusing it and then citing some source that someone has shown that it has high validity or so. But that does not mean that it has a high validity or accuracy in your case. So even if you use a dictionary-based approach, I think you should get a second opinion, and like at least for subsample of your text, you should give it to people and let people judge it, and then calculate something like an inter-rater reliability between the dictionary and people in order to really make sure that it's valid for your approach. So if there are any questions right now, I can take them about this dictionary-based approach. If not, I'll just go on with the next one, the statistical approach. So this is a second generation, was developed in the 1990s, and I think the best example you can think of is a spam filter of an email program, and this is also of a lot of effort was put into this statistical approach at that time. So when email popped up, and then yeah, I mean, we still have this problem of spam emails, and in the beginning, what was it called? Hotmail and Yahoo, etc. They followed a rule-based approach, and they had dictionaries with words which were kind of markers for spam. I will not repeat those words here, but I think you can imagine what words might be in such dictionary. So that these are indicators of spam, and if you have too many of these words in your email, it will be flagged. But then there was kind of an arms race between the people who spammed people, who created spam, and the internet providers like Google, and they always had to keep their dictionaries up to date. And at some point, especially when the cloud-based email services appeared, like a Google Mail, for example, they switched the strategy. And they said, like, can't we learn implicitly what words are associated with spam? And we can do that by the users can flag emails as spam or move them into the spam folder. And that's a feedback signal for us for a classical supervised machine learning approach. So every time when you move an email into your spam filter, this one will be used, or actually every email you have will be used to train a system to find out which words are associated with spam, or which word combinations are associated with spam or not. So the good thing here for Google is, of course, that we do this labor for free because we want to have a clean inbox, and they are profiting from that, and we are constantly training the system. Question for later. Okay. Yeah, I can answer it later. So the statistical approach is a little bit different. So this is a traditional programming. So maybe the rule-based or symbolic approach, which I've described earlier. But also when you write a program in Python, R, Starter, or if you develop a complex Excel sheet, which has some data and some functions, to calculate something. So that's what you do. You have input data, you have handcrafted rules created by an expert in order to produce results. For example, some accounting Excel sheet, for example. When you instead take a machine learning approach, this approach really turns it upside down. If you look at the arrows going into the box here and out of the box. So if you follow a machine learning approach, you take data and answers as input to produce rules as output. So what I've just described about the spam filter is you take data, emails, and answers, whether the user has flagged the email as spam or not. And the output of machine learning, the learning phase, is rules. So for example, probabilities that indicate whether when a certain word appears in an email, whether it's spam or not. These rules here don't have to be the same rules as here. Here, the rules are input, and the rules are created by experts. Here, the rules are learned inductively from the data and the answers. So it's really learning by example. This is also how we learn our native language. So we don't learn any rules. We don't learn any grammar. We are just exposed to lots of good examples by our parents and the whole environment. And at some point, we just pick it up. We get maybe positive reinforcement and so on. But we only learn the grammar rules after we have mastered our native language already. So this is exactly the machine learning approach. And then we have these learned rules. And once we have learned the rules, we can apply the rules again on new data, on other data. So for example, Gmail always updates a model with learned rules, and for every email you receive, this model is applied to produce results. So we have now kind of taken a shortcut around this knowledge acquisition bottleneck, this handcrafting of rules by learning the rules. However, it's not for free because we need very good quality input data, namely data and the answers. In the email spam example, it comes almost for free. And in other examples, you might have to invest in producing this training data. Okay, let me just, for later. Okay. Good. So this is the approach we are taking when we want to analyze the text. And the question is, okay, how can we, this is basically a statistical approach. Now we have this problem, we have our text. How can we fit the text into a data structure that is that can be processed by algorithms, so especially by mathematical equations, statistics. And it's a very simple approach. It's called the bag of words model and really has the name from a bag, as you can see here on the right-hand side. So when you throw things into a bag, you know it's unordered. It's chaos in there, and that's okay for us. So we represent text or a whole collection of text as tables. In these tables, every document occupies a row, and every word of our vocabulary occupies a column. And the values, the cells, for example, indicate the presence of a word in a document, or also how often a word has been mentioned in a document. And then you can do some more complex weighting schemes, give a penalty for very frequent words, etc. But these are minor details. The thing is that you lose word order in this. So you can see that here on the top right in this illustration, that you have lost the order of the words here, but I can also demonstrate that how it really looks like, this data structure. Typically, you do not use all the words. So you might want to remove some of the words because otherwise your table becomes huge. So it can easily get then 10,000 or 20,000 columns. If you also consider that maybe proper nouns, names of places and people, etc., might occupy a column in that table, you can easily run into the situation that you have more columns than rows, which is not desirable from a statistical perspective. So you want to be a little bit selective in which words you really put into that table, and you also want to harmonize the text a little bit. So So, for example, you can decide that you take only certain parts of speech. So maybe you do not want to have pronouns, and then you just ignore pronouns. You have seen on one of the diagrams, pronouns are very frequent, and maybe that reduces the size of our table. What you can also do is doing lemmatization or stemming. So that means you want to reduce the word to its dictionary form. So for nouns, you don't want to have plural and singular separate columns in that table. For verbs, you don't want to have past tense and present tense or third person as, etc., as separate columns in that table. And you also want to remove stop words like these. You can download lists of words where, yeah, the common sense is that these are stop words. Stop word means that they don't carry meaning. Words like the and I. And you might also want to do other pre-processing and filtering steps to produce your list of words, which then becomes the column of that table. So here's an example. We call that the term document matrix. So this is, of course, like just a glimpse at this matrix. You see here in the row headers, you see my texts, which I've used, and you also see that I have not included all of the words in the columns. For example, the word I have ignored here. It turns out that although this is really a simple representation, you can do lots of interesting things with it. And it's called the distributional hypothesis of computational linguistics, which says that words, let's start with the documents that have similar row vectors. So where two rows are almost identical in terms of these numbers here, tend to be related from a semantical perspective. And likewise, you can also look at two columns, words, and if they have very similar column vectors, these words are also closely related. So in the most extreme case, they could even be synonyms. So if you have built this structure, then you have a table, and then you can add, of course, all other, let's call it metadata. So for example, if we want to do sentiment analysis, we can get some ground truth labels about the classification of these texts. So that the first one, for example, is negative and the second two are positive in terms of sentiment. This is exactly what I called answers on the diagram. So the gray part is the data, the red part is the answers. We need this in pairs, and then we can train an algorithm on that. So typically you get these red column, you get it from people. So you have people labeling, let's say, 100 or 1,000 tweets about TV movies. And maybe that's already enough to train a system on that. And now in this representation, we can apply very old-fashioned statistics on it. So we can simply put this into a logistic regression model to estimate the probability that a certain text is positive or negative, given the appearance of words in that text. So y would be here our label, our dependent variable, and x, our independent variables. Typically, you have more than one. Didn't want to write down all the indices here. So a capital X is typically multiple. So these would be your independent variables or features. And this is your dependent variable, or target. So you can literally do that with logistic regression, so classic statistics. And yeah, we will demonstrate that later on, how well that works. And as I've said, often students are really disappointed when they take my natural language processing class that we're just transforming text so long until it fits into a normal logistic or linear regression model, and then it's just normal statistics from there on. And then people are really like, what? That is natural language processing? Yeah, that's the statistical approach or the machine learning approach to natural language processing. Okie dokie. Question. Would you call a statistical pack of words as a qualia? Oh, yeah, a good question. Is it qualitative or quantitative? A statistical analysis with bag of words. So no, in my view, I think that's quantitative. It's purely quantitative. It is completely bottom up. So you don't need to read a single of your tweets or text if you don't want to. What you typically do is you outsource the labeling via some platform like Amazon Mechanical Turk to people, or you outsource it to your students. And from that perspective on, I think the spirit of it is quantitative. Yeah, you're counting words, you're writing down the counts in the table, and then you put statistics on top of it. In my view, that's quantitative approach. Quantitative analysis of qualitative data, if you want. Okay, any more questions to the statistical approach? Okay, then let's move on to the newest generation, the neural approach uh, from neural networks. So we will now do deep learning on that. I hope you understand that I cannot, now it becomes a little bit more complex and I cannot teach all of that in like half an hour. And so I will take a helicopter view on this and just outline what is different from the neural approach to the statistical approach. But in the spirit, it's still similar. So it's a supervised learning approach where you need training data and you want to model the association between the appearance of words and a certain label you are interested in. And the state of the art nowadays, the neural network architecture is the transformer architecture. And the transformer has its name really from doing translation or transformation. So it can consist of two parts, an encoder part and a decoder part. The encoder part is really specialized in understanding the meaning of an input text, and the decoder part is specialized in producing output. We will not dive into the decoder part today, but the decoder part, when you look at the picture here on the right-hand side, this is GPT. Yeah, so because it's generative AI, it generates output text, it answers to you. But we also have transformer models which do not generate anything, which are not generative AI. And maybe some of you would recognize a word like BERT. So BERT was really the first a neural language model, which really sparked a revolution in the field. And it was an encoder-only model. And what we do in BERT is, so look here, you have to read this diagram from bottom to top. We have an input text. We have some special tokens here, for example, the separator token, which tells you the border between two sentences. That's minor technical details. The words are typically taken in raw format, so we do not do any pre-processing on them. And we also process this time the word as a sequence. So we are not disregarding the word order when we are using transformers. So that's a first innovation compared to the statistical approach. And the second innovation is that we also do not treat all the words as independent. So in the logistic regression, when you run a logistic regression on that term document matrix you have seen earlier, we have the assumption that the words are all independent of each other. But in the most extreme case, you might have two columns which have the same noun in plural or singular, etc. So there might as well be like a big dependence between them, and you want to exploit that, for example, synonyms, etc. And that's the second innovation, so that we are able to capture the meaning of words in a better way than in a pure counting way. And we are feeding these words. They get an ID internally, and then they are fed through a neural network. And this neural network has multiple building blocks. And the most important ones are the embeddings and the self-attention. And these are really responsible for these two innovations. Embeddings or word embeddings is about the semantics, capturing semantics of words. And the self-attention mechanism then considers the order of words in the text. And then you basically get as output also numbers in the end. And then you can use these numbers for various tasks, for example, for classification into sentiment, and you get an output very similar to the output of a bag of words model. So let's look a little bit at these two innovations, word embeddings. What are these word embeddings? So this is a very abstract concept. So a word embedding is just a representation of a given word in a dictionary by a vector of numbers. So just a list of numbers if you want. And you see an example here. So typically these are 300 to 768, so it's a typical number. Numbers, that's the dimensionality of this vector. So you have to imagine a high dimensional space. So here I have a three-dimensional space, so maybe you can see that, but in reality, it has many, many more dimensions. It has hundreds of dimensions, and words are points in this multi-dimensional space. And these vectors are created in such a way that words which are semantically similar are placed near to each other and have similar vectors. So here you see a visualization where I ask the system to display me the 10 most similar words to the word play. And you see here highlighted the words which are closest to play in this semantic space. It might seem a little bit weird because you say if play is in the center here, there are other words which are closer than, for example, hockey. This is just because we have a very high dimensional space reduced to 3 dimensions here. That's why we have problems with the projection. But you have to believe me that these are the 10 words which are closest to play. And what is interesting here, they don't for example, football and basketball are very close and they don't even share characters. So you really see this is beyond the syntax level here. It's more about how the words are used in contexts in documents, right? You can imagine, so these vectors are built by looking what words appear in similar contexts. Yeah, sorry, what's the question? Okay, yeah. So you're looking, and you can imagine lots of, for example, newspaper articles where you could even swap the word football to basketball, and it would even still make sense, the whole paragraph, for example. And if that's the case, then these words get very similar vectors. But this is done in a completely data-driven, bottom-up inductive fashion. So here's an example. I show you a semantic space with only 2 dimensions here because I'm not better in drawing. I couldn't manage to create a third one here. And I show you the 3 words with their vectors: wolf, tiger, dog, and cat. This is not random how they are located here. Does anyone have an idea what the dimensions might represent here? I have to admit it's a toy example, but on the next slide you get to see a real example. What could that be? X and Y axis. Any guesses? First answers are coming in. Wild animal, exactly, yeah. So on the Y axis, it could be that measures the wildness of it. So dogs and cats are domestic animals, whereas wolf and tiger are wild animals. You don't want to have them at home. Axis idea? Species, exactly. Yeah. I don't know the correct biological terms here, but you see the dog and wolf belong to a certain, like in the taxonomy of all animals, they are in some same sub-branch somewhere. And cat and tiger also are related. You know that tiger is basically a cat-like creature. Um, so this is exactly what I mean by that. And now imagine there would be more words in here. I've just highlighted four. All the other words are just hidden. You can do almost, you can calculate with that. What you can typically do is, so the vector here, if you go from the origin of your coordinate system to these points, that's the mathematical definition of these vectors. And then you can start calculating. For example, if you start at the wolf and subtract a dog from the wolf, so this dashed green line is exactly the same angle and length as the solid green line here. And then you add again a cat to it, you arrive at the tiger. And here again, this line is analogous to this line. So you can search, for example, for words here using analogies. You can say, oh, wolf is to a dog like a cat to a, and the system or the algorithm would answer here with tiger. And if you want to search for the leopard or the lion, you know you have to search somewhere here. It will be somewhere here. So this is how the semantics are embedded into these word vectors and how words are represented in these neural networks in the transformers. As I've said, this is a toy example, but this is a real example from a paper. So people have trained these models, have extracted the vectors from it, and then have tried to interpret them, have tried to say like, okay, is there some underlying meaning in the dimensions of this vector space? And here, this is a little bit dated, so probably it's not valid anymore. But what you see here are large companies and their CEOs on the right-hand side. So the x-axis here represents company versus CEOs. And I would say the y-axis captures some of like industry structures. If you look, for example, at Verizon and Vodafone, both telcos, and then you see maybe some like this is almost automotive, like very capital intensive, heavy machinery. Also United Airlines here, heavy machinery companies, and then maybe IT, finance somewhere in the middle. Viacom is also telco. So if you could probably here, you will find other telco companies, and then you can go there and then just go over here and search for the CEOs in that region. Typically, students have a very hard time understanding these analogies. Um, okay, so that's the first innovation. And the second innovation is this self-attention. I said, like in the bag of words model, it's called bag of words because in the bag everything is chaotic and unordered. But of course, we all know that the order of words plays a big role in this understanding of sentences and text. And that's also what is, yeah, that's one of the innovations. This is really basically the underlying innovation of all the GPT models. Attention, the very famous paper, Attention is All You Need by Vaishnavi, written in 2017, is what really started the whole revolution in this field. So once we have these vectors of each word, we do another thing. We update every vector, and we update the vector by looking what words are related to this word in the sentence, and then changing, like kind of calculating the mean or a weighted mean between these vectors. So for example, the vector of the word it in this neural network will be heavily influenced by whatever the vector of the animal is. So that really shows you that it here in this refers to animal, and it has really captured the meaning of this word in context. So in this sentence, because it I mean, the vector of it over all of English language would be probably very useless. But here in this specific sentence, it is really contextualized with all the neighboring vectors. Not all. Yeah. Okay. Yeah. I can do, of course. Okay. So that's self-attention is mathematically a little bit more complex, and we have not that much time today. So let's keep it like this. I think what you should remember is these two innovations of considering order and also considering the semantics of single words. And then another feature of deep learning or neural networks in general, not only in text processing, is supervised transfer learning. So what we had before, if you want to do sentiment analysis on movie reviews, for example, you have to train a model on movie reviews, on labeled movie reviews. Then you want to do sentiment analysis on hotel reviews, and then you have to train another one on hotel reviews because the vocabulary will be very different between movies and hotels. And then you maybe go to ratemyprofessor.com and want to rate professors, etc., and yet another vocabulary. So basically, you have to create a model, a new model for every task in every domain. This is not how humans learn, right? Remember how you learned how to drive a car. I think in Germany, the minimum number of driving hours you have to take is 20. And in the US, I know it's even less. And after 20 hours, people are able to drive a car without too many accidents. However, we still don't have self-driving cars on our streets in all around the world, although we have millions and millions of millions and millions of training hours, of recordings and sensor data, etc. So there must be something why we humans are much more efficient in learning than neural networks or machines. And this is transfer learning. At the moment we learn how to drive a car, we have a lot of prior experience in navigating the physical world, even as a child, knowing about physics, knowing about traffic signs, knowing about the behavior of objects when they are moving, how fast they can accelerate or not accelerate, how fast they can brake, etc. So we bring all this prior knowledge into the new task, and that's why we are so efficient. And transfer learning also enables that in the world of machine learning. So the idea of transfer learning is that we break our model into two parts. They're called the body and the head. And the body is really the part which is generic to a certain task. For example, the task of understanding English grammar, independent of the question whether it's grammar about reviews of hotels or of movies. And then the head is the specific part, which is specific to maybe your data set, for example, hotels versus movies. And we can reuse this body or adapt it somewhere, yeah? And this is great because now we can reuse models which other people have created. And we don't have to train these large neural networks from scratch all the time. So that is what makes it really fantastic for us also when we want to apply this. Okay. So this concludes my theoretical part, and for the rest, like 20 minutes, so I want to try it out. Yeah, I use topic bird. There is a bird version of topic modeling. I hope I'm not your reviewer. Topic bird is just like LDA is a topic modeling algorithm which assumes all words are independent, and then there's a version called topic bird, which really uses these embeddings instead of like normal word representations. Okay, so let me switch over to my presentation. What I have is I have 10,000 tweets of directed to airlines in the United States. So customers have written tweets to airlines, and I have 10,000. I think this data has been collected over the course of 1 week, about 7 different airlines. And I share the script with you, and you can reach it here. I'm clicking on that. So this is on Google Colab. So that's an environment where you can do Python coding in the cloud on Google's infrastructure. It's quite nice if you are working with collaborators. So everyone really works on the same document, a little bit like Google Docs, not that interactive. And I will execute this now. I have just executed, I will execute all of the script because it might take a couple of minutes. And in the beginning of the script, I'm loading from a CSV file these tweets. And I do some exploratory data analysis. So these tweets all have been labeled by people. I think every tweet has been labeled by 5 people to build some ground truth data. And then we can have a look at the distribution of sentiment here in the tweets. No surprise, most of those tweets are negative, of course, because I mean, most of the time when you write a tweet to an airline, you are complaining about something. And I think it's 80-20, so 80% of the tweets are really negative. So the data is coming here. So you see some examples. For example, American Air still waiting. Please respond as my flight leaves in 2.5 hours. Yes, we did make it home, but I am by no means happy. And you see that these are both negative, according to the judgment of the people, the labelers. 80-20. So this means if you always just predict that a tweet is negative, you will be right in 80% of the cases. So that's the baseline we have to beat, really. Everything else is basically worse than flipping a coin. So that's what you see here. So we must be better than 79.8%. Otherwise, it's not worth anything. And then here I'm showing Vader, how to use Vader. So Vader, you can have a Python implementation of that. And here in this code chunk, I feed the first tweet into Vader and see what comes out. And it tells me scores for negative, neutral, positive, and a compound score. You have to look up the documentation to see how the compound score is calculated, but that's if you really want only one score, then you take the compound score. And here we already see a problem that it thinks that this one is actually positive, this tweet, and the compound score is positive. It goes from -1 to +1. Here I'm rounding this, so I say, okay, wherever I have a score which is positive, I say it's a positive tweet. Otherwise, I say it's a negative tweet. If you look at the first 10 tweets, most of them are positive, but some are also negative. And then I can compare that now to the ground truth, which I have here. And it's 64 or 65%. That might look okay at first because we have the tendency to compare that to 50%, but you should not really compare it to 50%. As I've said earlier, if you just say every tweet is negative, you are correct in 80% of the cases. So that's actually a very bad score. And here I have a confusion matrix. So we are comparing the true label, so what the humans say, to the predicted label of my dictionary approach. And you see here we agree. Both say it's a negative tweet in 924% of the cases. Here we see it's positive, it's okay. But we see here, there's a huge numbers. In 600 something cases, our algorithm thinks it's positive, but it's actually negative. So that is exactly, I think, irony. People use positive words to say like, whoa, great, after 2 hours, I finally got my luggage. That's not meant in a positive way, right? So the dictionary-based approach here using Vader is really not good. I have to speed up a little bit, so let's go on to the statistical approach where I'm building this matrix, term document matrix, and then I fit a logistic regression model on top of it to do that, I first do a little bit of pre-processing. So I have my prepared text where, for example, past tense is turned into present tense, plural into singular, and so on. Then I build this matrix. Here you see a glimpse of this term document matrix. Of course, most of the cells are 0, but sometimes, yeah, here this word is used in that document. So these are all the words and these are all the documents. And then I'm training this logistic regression model and I get an accuracy score on my holdout data of 91%. Hugely more accurate than the dictionary-based approach, and also more accurate than our baseline of 80%. And if you look at the confusion matrix again, we had 600 something cases here in the top right, and now we have only 55. That's great. Yeah? However, you need the labeled data for this. You can only train such a model if you have, in my case, I used 8,000 cases for training. So you first have to produce these 8,000 cases. You can also look at the betas of your logistic regression model to see which words are really associated with positive and negative sentiment. So this is really the learned rules I've had on my slide. And it's, for example, it's very interesting that we see words like luggage with a minus 2.2. So it seems that this wouldn't be in any dictionary, right? That luggage is a negative word. But if you talk about luggage in the context of airlines, it's most of the cases negative. And then finally, a third generation. I mean, you have time to go through this notebook yourself and read all my texts here. Now I really use this transfer learning approach. So I'm not training anything. I download a pre-trained sentiment model from Hugging Face. Hugging Face is a superb library and marketplace on the internet where people are sharing natural language processing models, which they have trained on some data, and they say, okay, you can use that as is, or you can fine tune it on your own data. So there is a sentiment analysis model here. You can find all the IDs of these models on the website, and then here just change this. This model has been trained on 200,000 movie reviews. So it's quite a different domain, movie reviews and airline tweets. Different platform, different domain. But the good thing is it has been trained. I don't have to train anything, so I can just apply it out of the box without any effort. And it turns out it produces an accuracy of roughly 90% in this case. So a little bit worse than the back of words model. And you see also it's a little bit worse than capturing the irony here. However, on the positive side, you do not have to put manual effort in here. I mean, you might want to label some of the examples by hand to be able to calculate such a metric here, but it's much less effort. So I think a very good trade-off between effort and utility here. Okie dokie. I think I stop sharing now here, and let's use the rest of the time for potential questions.